Good evening, everyone. My name is Renuraman Sahu, and I'm from Indian Institute of Science, Department of Instrumentation and Applied Physics. In this module, we'll be discussing about the fundamentals and applications of plasmonics. Plasmonics, in general, it is a major field of nanophotonics, and just like uh, we have a trend of miniaturization, there is a trend of making devices as small as possible. For example, in case of the transistors, we wanted uh, we wanted the devices to be as small as possible and to be incorporated in a chip. Similarly, plasmonics has allowed us to make photonic devices to be incorporated in a very small length scale. So it mostly uh, deals about the interaction of light with the electrons in a metal. In this module, what we are going to do is to learn about the fundamentals, starting from the physics point of view, and from there on, we'll go to advanced topics like surface plasmon, polaritons, and local surface plasmons, and then we'll look into some of the applications. So what we expect from this course is that first we'll have a basic understanding of the plasmonic phenomena, what is happening in particular these two, as I told, the surface plasmon polariton and localized surface plasmon, and then we'll go into some of the applications. And so in this lecture series, what we will be doing is we'll be deriving all the equations from Stephen A. Meyer. So the name of the book is also uh, the name of the book is Plasmonics, Fundamentals and Applications. And then the concepts that we learn as we go through, we will try to relate it with the current research trends what is going on. So what is plasma? So plasma is a gas of charged particles. For example, here, what you see on the screen is a streak of lightning. So what is happening here? So when there are charge separation happening over the clouds, so there is a huge potential difference created, and in that huge potential difference, uh, because of that huge potential difference, there is a very high electric field, and in that electric field, the gas molecules of the atmosphere, they get ionized, and uh, because of that, because of that charge separation, there will be a bunch of electrons and there are a bunch of ions. So they constitute plasma. Similarly, this is the image of solar surface, and here you can see there is this Earth surrounded by a magnetosphere. So what is happening here is because of very high thermal energy, the electrons of the gases that constitute Sun, mostly hydrogen, the electrons cannot uh, stay there in their orbital. So it is a gas of protons and electrons. So that is an example of plasma. So, mostly when we think of plasma, like we have to think of it as a gas of charged particles. Similarly, uh, there is a very particular type of materials called metals. So metals, these are one of the very initially studied materials. When people started having questions like why are some materials conducting to electricity and why are some not, what makes some material uh, like shiny and lustrous while others are not, and what makes some materials malleable and ductile while others are not. So all these questions, it could be explained by considering that there are bunch of free electrons in metals. So metals are very special class of materials. So like, and we can think of metals as uh, they are materials with abundant free electrons. Now, in atomic theory, what we have learned is that metals uh, in uh, in any atom there is a abundant amount of free space, uh, and electrons, if the like the analogy that is usually given in textbooks is that if you have a cricket ground as the size of the atom, then the cricket ball is the size of the nucleus, and the rest of the volume, that is mostly empty, or you can think of it as that are occupied by the electron wave. So mostly the material is empty except for very small negligible spatial volume, and therefore the electrons which are free to move around in the bulk of the material, they can be thought of as it is a gas of free electrons. So electrons in metals, since they are also charged particles, negatively charged particles, they can be considered a plasma. And in this course, what we are going to do is we are going to see how these free electrons in metals interact with light. So, what is light? Light is basically an electromagnetic wave. And in electromagnetic wave, what do we mean by electromagnetic wave? It is just uh, some electric field and magnetic field coupled with it. So in any electric field, the charged particles, they will start to they will like if it is a positively charged particle, it will move along the electric field, or it will experience a force along the electric field. If it is a negatively charged particle, it will experience a force opposite to the direction of electric field. So basically, this electromagnetic fields are the driving force for the charged particles, or the uh, Lorentz force which drives the charged particles into motion. Similarly, when we shine light on a metal, then the free electrons in metals, they get some force, they experience some force, and that force makes the electrons, they move in the metal. So what we are going to study in first few lectures of the course is that the electromagnetism of metals. So it is not quite different from the the usual methods, but what makes metals interesting is the presence of these free electrons, and that we'll see in due course, like what are the effects it can give. And the study of oscillation of these free electrons in unison in response to this electromagnetic field, it is called the plasmonics. So the oscillations, so we have studied in quantum mechanics that for example, in simple harmonic oscillator, the oscillations can be quantized. Similarly, the oscillations of uh, like uh, if we try to speak quantum mechanically, then these oscillations can also be quantized, and that formalism is called like from that formalism, each quanta of this oscillation is called a plasmon. And just like we have this fields called electronics, spintronics, where we try to manipulate, uh, for example, in electronics, we try to manipulate the motion of electrons to get some device application. Here, what we are going to do is we're trying to, in plasmonics, what we usually do is we try to engineer the material in such a way that we have a precise control on this oscillation of these free electrons, or basically uh, this oscillation of free electrons uh, can be precisely tuned and engineered as per our will. So, and these applications, this come under the purview of plasmonics. So just like electronics, they exploit the motion of electrons. In spintronics, they use the spin of electrons to get some device applications done. Here we will use the plasmons, or the collective oscillations of free electrons uh, in a metal. So plasmonics, it constitutes a major part of nanophotonics. So most of the material, almost all the materials, it can be divided into two type of materials, metallic and non-metallic. And uh, the basically this engineering this free electrons of the metals, they or what we term as plasmonics, they constitute major part of nanophotonics. Why nano? So nanometer, it is the scale of 10 to the power minus 9 meter. So, uh, so when you shine some light onto a metallic particle, a metallic nanoparticle, the electrons will start oscillating. That means the electromagnetic energy has been converted to the motion of the electron. Now, electrons are charged particles, and whenever some charged particle will accelerate, so an oscillation is a type of accelerating motion. So, whenever these electrons will start to oscillate, they will give back some radiation in terms of like in as a photon. So again, that photon, it can again, so photon is nothing but an electromagnetic field that can create the electron to oscillate. So there is this self-sustained system, and so what it effectively leads to is the confinement of, so this phenomena will effectively lead to confinement of the electromagnetic fields in very very small volumes, smaller than very small volumes. Like when I say small, it is uh, uh, small with respect to the wavelength of the light. So uh, so we can confine electromagnetic fields into volumes which are uh, like of the order of some fraction of the wavelengths of the light. And this happens by the interaction of electromagnetic radiation and the conduction electrons at metallic interfaces. So whenever there is this interface of a metal and a dielectric, the dielectric can be even air or vacuum also. So so light will fall on the metallic interface. The electrons of at the metallic interface will start oscillating. Then they will again give back light, and that they will give back light uh, because electrons are the charged particles, and they will oscillate. And when they will oscillate, or oscillation is a type of acceleration, and we know from basic electromagnetism that whenever a charged particle will accelerate, it will give back light. So there is this self-sustained system going on. So this is what that happens, that at an interface of a metal and dielectric, whenever a light falls, there is this enhancement of electromagnetic field. Okay, and and this electromagnetic field, they can travel certain distance along the interface. That is called surface plasmon polaritons. Polariton is nothing but it is just another word for light. So light can is coupled to the oscillation of electrons at the surface. That is why it is called, it is just a surface plasmon polariton. So so qualitatively we can think of it as, so at this interface, light is falling on it. It is making the electrons here to oscillate, and this oscillation is giving back light. That light is again creating the oscillation of electrons, and thereby this uh, light is coupled with the electrons, and that coupled electron oscillation and light. So polariton is nothing but another term for the light, which is coupled with the electronic oscillations. So now instead of saying electronic oscillations, we will say it plasma. So it is called a surface plasmon polaritons, and they can travel along the interface in a self-sustained way up to certain distance. So that is surface plasmon polariton, and we'll see how this comes up from the classical Maxwell equations and uh, classical electrodynamics. So there is another concept called localized surface plasmons. So when we have this interface, this is a planar interface. The this oscillation of electrons, they can like travel along the interface. Now when we have two individual, so this is a dimer, two particles. In that case, what happens is oscillation of electrons, they cannot leave this boundary. The electrons are inside this metallic volume. So what will happen is the electric, so it is like a kind of a standing wave. So electrons are oscillating here, and this oscillating electrons is giving back some light or the electromagnetic wave, and that causes the electrons here to oscillate, and again that will give back some electromagnetic radiation, and this will oscillate. So this self-sustained system, that will create a very highly intense electromagnetic field localized into this small volume. Okay, and that is called uh, localized surface plasmons, or LSPs. or sometimes so at the resonance condition it is called localized surface plasmon resonances. So in like this, they have very important crucial applications in sensing, and there are a lot of fields. Just to motivate you, like what are the things going on in the field. So I'll show you some of the like current research work. Uh, for example, here. So here you see a polymer, and in this polymer what we have is some of the metallic nanoparticles are embedded in it. And when these are, and there are gap, so in between that, in between this nanoparticles, what is there, you have this gap plasmons, or the and the resonances are sensitive to that gap. So this is just an application of what plasmonics can do. You see the color changed from pink to green, and then when you relax it back, it changed from green to pink. So there is another sample here. It is a similar sample. Here you can see that color is changing from blue to yellow. So this is an example of visual sensing. So not only this, what more we can have is uh, so there are work in, for example, in energy harvesting and photonic devices by using this plasmonics. So remember that we have confined, so using this coupled electrons and photons, the electromagnetic fields can be confined to very small scale, and then that in that the energy confined in that small volume, in that nanoscale volume, they can be used for different applications, for example in solar cells, in light emitters, and in sensors. Okay, in photonic devices and energy harvesting it is quite useful. Furthermore, there are some devices called meta surfaces and meta atoms. So what are these? These meta surfaces and meta atoms, these are sub-wavelength nanostructures. They are made using uh, like precise lithography systems, and what they can do is they have like uh, uh, a lot of applications in, for example, uh, nanoscale lenses, or some kind of filter, uh, or uh, uh, or holography. So they have or maybe some kind of polarizer. So all the optical components that we see, uh, the for example beam splitter and all, there are a lot of optical components, right? And these optical components, they occupy some bulk or some volume they occupy. But with these metasurfaces, like if we design these metasurfaces and metaatoms smartly, then all those functionalities of photonic devices can be engineered by these metasurfaces. So there is so this is a like very popular field uh, which is going on these days. People are working on metasurfaces and metaatoms for various applications, and there are things like vortex beams and uh, so this uh, uh, the interaction of this particular metasurfaces and metaatoms, they mostly in many cases they use plasmonic materials or like uh, active substances, which results in multiple functionalities. Furthermore, there is like plasmonics have also been used in biosensing, and there have been applications in, for example, in cancer treatment. In so and there are so many applications for this plasmonic materials. But the important thing is like what we will. So these are like some of the motivation to study plasmonics applications. Of course, is a very big motivation. What we want is like what we will do in this course is like keeping these applications as a like long term goal. So we'll not go into each and every applications. We will focus on building our fundamentals to understand these phenomena better, so that we can uh, we can use our skill later to design or to cater to some kind of very specific applications that we have in hand. So what is plasmonics? So, so as I told you, it is just the oscillation of electrons in response to the electromagnetic field. And how are electromagnetic field defined? Electromagnetic field is nothing but you just have some Maxwell equations and some material, and you define some boundary condition for that material. You define some boundary conditions. Everything classical. So all this, like one of the best book for classical mechanics is this J.D. Jackson, Classical Electrodynamics. So, so we have Maxwell equations which are classical, and some material properties and some of the boundary conditions, all the classical stuff. And uh, just because they are classical, that doesn't mean they cannot do wonders. As we saw in the previous example, it can do a lot of things. Like for example, design of meta surfaces. So what Bill Barnes is one of the uh, one of the pioneers in plasmonics or plasmonic meta surfaces. He says that it can turn Snell's law on its head. For example, using this meta surfaces, what people have done is they have done something called optical cloaking and some other optical cloaking. What it means is that it will make your substance which is behind your meta surface to completely meta material to completely disappear, or squeeze light into the places which is 1/100th of its wavelength. So, uh, so this talks about the volume in which the electromagnetic fields can be confined to. So these are like quite wonderful. So it is quite wonderful that we're able to achieve these things by using uh, just by this uh, classical stuff, the Maxwell equations and the boundary conditions for some material. Here we are not talking about any like very big fundamental particles or not very great cosmology, but there are a lot of surprises and wonders, and we can design and engineer uh, lot of material with wonderful functionalities. So there are so plasmonic research, it started around 1952. 1952. In 1950s it started, and it started gathering up with advancement in the state of art fabrication methods. So fabrication is really important. Fabrication methods, particularly in the domain of nanofabrication. So as nanofabrication it increased, we could build structures that are comparable of the whose feature sizes are comparable to that of the wavelength of the light, and hence we can engineer how precisely the light will interact with this material. And then we started having very highly sensitive characterization techniques that tells about the response of this uh, plasmonic materials. And uh, more than that, so before we go into fabrication, so fabrication it requires lot of skills and resources, and as well as the raw material. So before going into that, so it is just, so as we discussed in the previous slide, it is nothing but just uh, uh, just the Maxwell equations. And these Maxwell equations, they are nothing but a bunch of differential equations and partial differential equations, and they can be solved uh, by computers. And with increase in this computing power and speed, what we have is, so even before fabrication, we can determine what would be the properties of these materials beforehand. Okay. And there is this wide range of potential applications as we saw before, like solar cell, high resolution spectroscopy, and there is one very important application which I just missed out, this surface enhanced Raman spectroscopy. This is one of the field which got revolutionized by plasmonics, and in drug design, drug delivery. So there are a huge range of potential applications, and it is these applications which actually drive plasmonic research into full fledged. So we'll first discuss about the electromagnetics of metals, because it is in metals where we find the free conduction electrons. So we start with the Maxwell equations. That is the starting point. Here, what is important to note is that before going into Maxwell equations, we have to understand that Maxwell equations are classical equations. So Maxwell equations, these are classical equations. What it means is that you don't have to use any quantum mechanics. But what we have learned that in quantum mechanics, it is the science about, or it is the study when we go to nanoscale, at very small scales, uh, like we have to use this quantum mechanics. Why is it that for in this case, when we are talking about this metallic nanoparticles, we are only the classical equations are sufficient for it. So the answer to that is metals have very high electron density. Now, like how does this electron density help? Let us try to understand through this. Suppose we have, uh, so let us try to understand this concept with respect to a particle in a box. So, so we have a nanoparticle. Let's say that this is a nanoparticle. It is a certain spatial volume. It has a certain volume, a certain spatial extent. Now, whenever you confine an electron into a finite volume, confinement of electron or any fundamental or any particle, so to speak, uh, into a finite volume, that leads to quantization. This naturally indicates that we have to, like this suggests that we should be using some uh, quantum mechanics. But now what happens is that if you have, let's say this is the some band structure, okay, some band structure of electron in that finite volume. Now you have, if you start to bring another electron, if you bring another electron, then what will happen? Then you will have the each band will have two. So these are the energy levels. Just right. And these energy levels are quantized because the particles are confined in a finite volume. So if you have three electrons, then what you have is you will have, so each of the discrete line there will be, so there will be some kind of breaking of degeneracy, and you will have the three lines. Now the point of having a metal is that metals have very high electron density. For example, in gold and silver, we have of the order of 10 to the power 28 electrons per meter cube. Okay, so this is a very high density of electrons. And what happens is when you have very high density, so even in a small volume, you have even a, so density, number density is of the order of this much. So even if we have a small volume, what we have is the number of electron is very large. So due to high density, and larger the number of electrons, larger will be the number of energy levels and smaller will be the spacing between the energy levels. Now, when you increase these electrons to a very, very large number, so if you have, let's say, n of these electrons, so what you will start to see is that there is a kind of band coming up. So there is a band of very, very closely packed electrons. Now, if one of them is half filled or like not completely filled band, so this is how the band of electrons will take place. But now, when you have a large number of electrons, the spacing between, so if we try to zoom into this, if the spacing between these two energy levels, if let's say that is delta, okay, if delta is if delta is less than kBt, the thermal energy, okay, if this energy spacing is very, very less than kBt, then we can treat the particle in the framework of classical electrodynamics. On the other hand, if delta is comparable to kBt or delta greater than kBt, then we need to use quantum mechanics. But what happens is, since we have very, very high number density of electrons, the high number density of electrons will make this energy level spacing so less than the kBt. What is kBt? It is around 26 milli electron volt. 26 milli electron volt at room temperature. Okay, so this energy spacing is very, very less than the thermal energy, and that is why we can use classical electrodynamics to explain the plasmonic phenomena. So this optical properties, what we observe from our experience is that metals have very high reflectivity up to visible frequencies. So that till up to visible frequency, metals will not allow any electromagnetic waves to pass through them. And the application of this property is that cladding layers in waveguides and resonators uh, are built by these metals. And in low frequencies, by low frequency, what we mean is that microwave and far infrared frequencies. So in these frequencies, metals are very highly reflective. But on the other hand, when you start going to the UV frequencies, the metal acquire a dielectric characters. For example, like the alkali metals like silver, potassium, uh, they are UV transparent. So if you shine UV light through them, it will just pass through these metals. So let us start with the Maxwell's equation. So the Maxwell equation, the first equation is the Gauss law, and the divergence of D is the dielectric displacement, and D is the dielectric displacement, and if you take the divergence of that, what you obtain is the external charge density. So this external charge density is like we are injecting some charge into the material so that the fields in that will get modified. And then the next one is the uh, Gauss law again. So divergence of B is 0. Okay. Then we have the Faraday's law. The curl of the electric field E is the negative partial time derivative of the magnetic field induction. And then, so that is the Faraday's law. And then what we have is the Ampere's law, which says that the curl of H is the magnetic field. So curl of the magnetic field is uh, it is equal to the current, the external current density plus the time derivative of this dielectric displacement. Okay, so what we have is we have sources here. So this is the source, rho external. This is the source. The fields here, the fields are the electric field, the magnetic field induction, and this is the magnetic field, and this is the dielectric field intensity, the dielectric displacement. So the dielectric displacement and H, the magnetic field, they are the material characteristics. So they have the material information in them. On the other hand, uh, so what we have is this field, the electric field and the magnetic field induction or the magnetic flux density. They are the fields to which the electrons and protons or any charged species will react to. And after, so when you give or sign some electromagnetic field on material, then that material itself will show some response. So it will get magnetized itself, or it can get polarized itself. So depend on that, there will be a new set of so because it is the charged particles that orient themselves, and because of that orientation, the resultant fields will get modified. Okay, and the modified fields are this D and H, and they have the information about the material property. So we have two set of charge and current densities. So one we have talked already seen in that Maxwell equations. These are the external charge and external current density. So why external? Because we want to distinguish it as that we have a system, and from outside we will be injecting in charge and will be injecting in the current density, and then there will be certain response. There will be certain field response to the material, and that field response uh, so you inject rho external and J external into the material, so that will change the fields inside that material, and because of the change of field inside that material, the material will induce some of its own charge and current density. So the total charge and current density that we'll measure is the sum of this external and internal charge density and sum of the external and internal current density. So what we have now is the fields. So we know how the fields are related. So these are the fields are related to the sources. Okay. Now what we want to do is, uh, so we want to look at the different fields, how they are related. So so how the material exactly responds to the incident field? We have this electric field. Let us start with the electric field. We have electric field E. Because of the presence of this electric field, what will happen? Suppose this is a material. Okay, in this material there are certain kind of molecules, and that molecule will have a plus charge and a minus charge. Because of the presence of this electric field, what will happen? There will be a charge separation going on. At certain region there will be minus charge, certain region there will be a plus charge. Okay, so now there is a resultant polarization. So this is for one molecule, let's say, and there are n molecules per unit volume. So there will be a net polarization of the molecule. So this net dipole moment per unit volume is called polarization vector P. It will have a direction. The direction is along the majority of the polarizers, and the way it is related to the resultant field is, so epsilon naught E. Epsilon naught is the electric permittivity. and the dielectric displacement d is nothing but epsilon naught E plus P. Similarly, we can define the same for the magnetic field. For the magnetic field, we define something called H, which is the magnetic field, and it is 1 by mu naught B. B is the magnetic field induction or the magnetic flux density, and it is this B to which the charged particles will uh, uh, it is the B which the charged particles uh, respond to. And because of the presence of this B, the charged particles will start responding, and because of that response, what we have here is a net magnetization of the field. There is a net magnetization where M is the net magnetic moment per unit volume. So what we have here now is the P is the polarization vector, and because of this, the electric field generated due to the individual dipole moments in this polarization vector, we see a change of the overall electric field. So now what we are going to do is we want to see that this P is related to the internal charges P as rho is equal to minus divergence of P. There is a very nice illustration. It is there in Griffith's electrodynamics. So it is the negative uh, divergence of the polarization vector is what we have as the uh, internal charge density. Similarly, now we can use conservation of charge. Conservation of charge says that divergence of J equals minus. Now we are going to use this. This is the continuity equation. Now what we are going to do, we will take this relationship and we'll take the divergence. We're taking the divergence. Now we know that from Maxwell's equation, so divergence of T is rho E x T and epsilon naught divergence of E. This we want to find out, plus this is from this particular equation, from this equation minus rho. So this gives us what? Epsilon naught divergence of E is equal to rho plus rho ext, rho external, and rho external is nothing but now we'll substitute the values. Now we have, and this is nothing but rho total, and what we have is, so this is the usual form of Gauss law that we see in the textbooks. Now what we will be doing is, we want to find out how what is the consequence of this so we got to know about how the free charge is there in that, uh, so what is the relation of the free charge in, free charge is rho is equal to minus divergence of p, or the polarization vector. What we want to do now is how this is related with respect to the charge density, or the current density. This is the charge density. So what we are going to do, we will use the continuity equation. The continuity equation is divergence of J is equal to a plus partial derivative of rho equal to, this is nothing but conservation of charge. And conservation of charge is giving you this result. What we are going to do now is this, instead of J, uh, we we are going to use, instead of rho is equal to minus divergence of P. So what we have here is divergence of J plus rho dot T of minus divergence of P is equal to 0. Now we can interchange, at least in this case, this partial derivative with respect to T and partial derivative with respect to the space. So what we have is J plus J plus, so from here what we have is divergence of J minus this implies J is equal to, so this is how the internal current density is related with the polarization vector. So remember that this polarization vector is the material property or response of the material. Next, what we have is, with this approach, all the microscopic electric fields will have all the polarization effect. Okay, so when we define this current density as this partial time derivative of the polarization vector. Now what we have is, we will limit ourselves to the linear and isotropic media and non-magnetic media. So for that, what we have to do is, uh, so we'll take the, now we limit ourselves linear, isotropic and non-magnetic and non-magnetic media. Now, so what does this mean mathematically is that, so the response, so we have seen that this field D, or the electric displacement, it is a response of the material to the electric field that we are signing, that is displacement. This is the modified field. When we put in some electric field, the material responds by saying, by arranging or rearranging its molecules by giving some polarization vector, and the field due to that particular polarization and the electric field, they will combinedly give this displacement vector. So what we have is, we say that this is basically the response of the material. So when we say that D is directly proportional to the electric field, then we say that material is linear. So this is how we define a linear material. Okay, and there is another way to say the same thing. So this is about, the material is linear, and epsilon is the, so this was the electric permittivity, or electric permittivity of free space, and epsilon is the relative permittivity. And remember that this is unitless. This doesn't have a unit. So similarly, for magnetic field, what we have is, for the magnetic field, we define the linear media as B is equal to mu naught mu H. Okay, so this defines linearity of the material. So another issue is, so linearity, and H is the magnetic field and B is the magnetic flux density, and here mu is relative permeability. Okay, and for non-magnetic material, mu is 1. So there is another way to define the linear relationship, which is equivalent statement, but it is just a different way of representation. And the way we do it is like by defining. So there, so here what we did, we defined the electric displacement as directly proportional to the electric field. Now we'll say that the polarization vector, which is induced in the material because of the incident electric field, that is directly proportional to the electric field, and the constant of proportionality is called chi, and this chi is your electric susceptibility. So if you put everything in this equation, so what we have is D is equal to epsilon naught E plus P, or what we can do here, D is equal to epsilon naught E plus P. D, we say that for linear material, what is D? It is epsilon naught epsilon E, and E is your relative permittivity, is equal to epsilon naught E plus, for linear material, the way we defined P is epsilon naught chi E. What we can do here is we can take epsilon naught E common, and we'll take all these two terms to the left hand side. What we have is this can only be 0 if epsilon is equal to 1 plus chi. So if you know the susceptibility, you know what is the permittivity, relative permittivity of the material. Okay, and we are going to use this particular fact for derivation of the material properties, like free, what is the susceptibility of the free electron gas, or what is the susceptibility of uh, like a free electron gas with some interband transitions. So all those questions we can answer with this particular relationship. So this is going to be used later. So what we have seen is this epsilon is the material property, epsilon, and hence chi, or the susceptibility, it is the material property. There is another equivalent material property that we study, it is called the conductivity. And conductivity is related to, so for example, P here, P was related to what? P was related to your, so if you remember this, the charge density, internal charge density. Here, conductivity, it is related to your J equals sigma E. So conductivity, it tells you about the relationship of the electric field and internal current density. So this was internal charge density. Now what you have is internal current density. Okay, and you remember that this current density J is also related to P by this relationship. Okay, so basically, whether you know sigma or you know epsilon or the relative permittivity, so they are the equivalent quantities. Okay, so conductivity, this is the relative permittivity and sigma conductivity. These two are equivalent quantities, and I mean equivalent in the sense there is a certain relation, so they are not independent of each other. So there is a relation which relates these two. Okay, not, so basically, if you know permittivity, you know conductivity. If you know conductivity, you know permittivity. Not independent quantity. So we are going to derive what is this permittivity, what is the relationship between these two. Okay, uh, in a more general sense, not so in a general way, we want to derive the relationship between these two. And so the way they have been used experimentally is, so these are mostly used in low frequencies, like till RF or microwave frequencies. but these are used in from optical frequencies and upward. People mostly use the relative permittivity to quantify the things. Nevertheless, uh, these two quantities are equivalent, and we are going to derive the relationship between the two. But before that, what we are going to uh, will will mark a note of caution here is that the point is that all EM phenomena, since sigma or the conductivity equivalent or they are related to each other, they are not independent of each other, are related to each other, all electromagnetic phenomena can be described either by uh, by either of them. Okay, so but we have to keep in mind that what are these two? These two things are they came directly from the assumption that the material under consideration it is linear, so that these quantities, the source, the this is sigma A, which is directly proportional to the electric field, and the displacement current that is also directly proportional to the electric field. So these two equations, these two quantity, they come about by assumption of the uh, linearity of the media. Okay, and in this form, there is no spatial or temporal dispersion. What it means is that the electric field at a particular time or at a particular point is instantly affecting what is the current density at that particular point or time. Okay, but it can also happen now. Uh, Now we'll take into account the temporal and spatial dispersions. What it means is that so this current density and displacement current, these are the response of the material. Okay, and they can uh, so it can happen like from these equations, only these two equations. What we are saying is that the electric field at a particular space, point, and time, they affect instantaneously what is the uh, current density and displacement electric field or the displacement field. But it can also happen that the electric field at, let's say, position r prime t prime, so at some position and time is creating a response or the internal current density at some different position r, where r is different from r prime, and t, where t is different from t prime, and the response of the material to this electric field is given by this, the response function is the conductivity, and that conductivity now depends on the difference between these position vectors and the time difference between them. So this is an impulse response function. Okay, and we integrate over all the electric field points. So integrate over all the time, integrate over all the r, so that you get the net electric field. And okay, and and why we can integration is just means that we are adding the contributions, and addition is uh, valid because of the linearity, assumption of the linearity. So because these equations are linear, we can integrate along all the uh, time and space. So this is taking the temporal. So when we integrate over the time, it is taking the temporal dispersion into account, and when we integrate over the space, it is taking the spatial dispersion into account. Similarly, we can write the other equation as well. D at some r and t is epsilon naught and epsilon r minus r prime t minus t prime and e r prime t prime dt prime dq r prime. Okay, here epsilon naught, epsilon and sigma are the impulse response functions. Okay, so here one thing to keep in mind is that, so when we are integrating over some time frame or this space or this volume, what we have internally assumed is that, so when we are integrating over this spatial volume, let's say, okay, then this volume is greater than the lattice spacing, so that so there are no fluctuations of the electric field at the level of the lattice spacings. Okay, and what we have also, so what we are saying that all the length scales are uh, significantly greater than the lattice spacing. So that inhomogeneity due to that lattice spacing, that we are totally ignoring. Okay, and we are ensuring homogeneity. How we are ensuring homogeneity? By that when we ignore about that lattice spacing, and the impulse response function, they also do not depend on the absolute positions, rather they depend on the impulse response function are this, they depend on the difference of these positions and difference of time. Okay, they are not absolutely dependent on the they are not absolutely dependent on a particular position. Okay, it is the difference, that difference of these positions and the difference in time on which these are dependent. Now this is crucial because this will, so as we'll see later, that when we do a Fourier transform of it uh, to get the uh, relationship in the frequency domain, uh, it is this difference of space and time that will allow us to decompose and simplify the equation. Okay, so now let us try to do a Fourier transform. So this is basically a particular form of this type of integrals are called convolutions, and in the Fourier domain, the convolutions, they turn into multiplication. So I hope you all know this principle, that on Fourier transform, convolutions turn into multiplication. Okay. So when we do the Fourier transform with respect to space and time, for example, if you want to find what is the Fourier transform of let's say J R T, and we want to Fourier transform it to J K omega, where how do we do this? The procedure is this: J, I'm just giving a tilde just to so that it is the Fourier transform, or J K is the wave vector and omega is the frequency. So this is in the frequency domain. Frequency when both space and time are both Fourier transformed. So what we have to do is just integrate with respect to time and integrate with respect to r with e to the power I k r minus omega t j r t. So this is the definition of Fourier transform. Let us try to do this and see what we are getting. So what is j? Uh, j of rt we can replace using j rt is equal to integral. So we are going to substitute this integral of j dt prime. So we'll just put it in here, and what we have is, okay. Now we're going to do a kind of rearrangement. So what we will do, we'll multiply with e to the power I k r prime minus omega t prime, and what we'll do is again multiply with e to the power minus I k r prime minus omega t prime. So basically what we are doing is we are doing nothing, we are just uh, like multiplying and dividing the same thing, which will just result in 1. Okay. So if we just rearrange this, what we obtain is, so I'm just trying to rearrange this guy. So we have dt prime here. So after dt, d cube r, and dt prime d cube r prime. Then what we are going to do, we'll try to keep this and this together. E to the power I k dot r minus r prime minus omega t minus t prime. Okay, and here we'll write sigma r minus r prime t minus t prime. Okay, and then what are the rest of the term? Rest of the term, it is just this e r prime t prime and e to the power I k r minus omega t prime. Now what we will do, keeping t and r fixed, we will first integrate with respect to uh, t prime and r prime. So note that this is the difference, and since we are keeping this t and r fixed, we can think of it as t prime minus t and r prime minus r. Okay, so what we have is, if we take only this quantity, integration of time and space for this, and remember that we are first keeping t fixed and integrating t and r fixed and integrating over space, the primed space time. What we have here is, then we can do a change of variable as t minus t prime and r minus r prime, because t and r is fixed. So uh, just to uh, fill in some of the space, we'll just, you can, so this is equivalent to writing, so this part, it is equivalent to minus t prime. Since I am putting a minus here, I can put a minus here as well. Okay, so and this is equal to d. So at a constant, so this step is valid if I'm keeping this t and r constant, and this is t minus t prime d cube r minus r prime. After this step, what you can do is, you can do a change of variable. This t minus t prime, you can write it as some other variable. So all this t minus t prime will get uh, get into some other variable, and when you do the integration, what you have is, you see the quantity underneath this green line, as above this green line, is just the Fourier transform of sigma, isn't it? So what we will just write is, in the next step, we'll do a Fourier, just write it as the Fourier transform of sigma. It's equal to integral dt d cube r and e Fourier transform of sigma is sigma k omega. So how we're getting to know? By this definition. This is the definition that you were using. Like in general, it may not be a vector function. Like just, we can just write it as some function. some function f. This is also some function f. So here f k omega is the Fourier transform of f of rt, and this can be a vector function as well, and any other function you can consider it. So using this Fourier transform formula, what we are going to do is, so what we have changed this. Similarly, we can change this as well. K omega e of r prime t prime e to the power I k dot r prime minus omega t prime. So now you see this sigma k omega, it is independent of t and r, right? So it can just go away from the integral, it can go out of the integral, and what we are left with is, so sigma k omega, it went out of the integral, sigma k omega dt dq r prime. So I'll just rewrite here j of k omega is equal to integral dt dq r prime, sorry, r. Oh, here we need to okay, here we need to keep the primed coordinate. So this integral, okay, this has been done with respect to uh, dt and dr, not with respect to dt prime and dr prime. We need this dt, this primed coordinates to integrate this. So the first integral was done with respect to t and r. The second integral, it is being done with respect to k and omega. And so what we have is sigma k omega integral dt prime d r prime e r prime t prime e to the power I k dot r prime minus omega t prime, and this is the definition of the Fourier transform of e of k omega. So what we have done here is, we took the general spatial dispersion, spatial and temporal dispersion into account, and what we have derived is, in the Fourier transform coordinates, we have a simple multiplicative relation between the conductivity and the uh, electric field. It is just a multiplicative relation, and this is just because of the fact that we started with a convolution, and you see here the fact that here we can use e to the power I k and e to the power minus I k r minus omega t, that helped us to rearrange into this, uh, that allowed us to rearrange into this difference, and because this difference is there, then we integrate these two terms with respect to t and r, and this came out as the Fourier transform, and whatever we're left with, that is the Fourier transform of E. Similarly, exactly the same procedure, what we can do the same with the electric displacement. So epsilon k omega e k omega. So we have these two equations now. Now, what we're going to do is we have to recognize that any time domain signal, for example, uh, so what is the Fourier transform of a function? Fourier transform of dou by dou t. So, uh, so if we have a function uh, which is differentiated with respect to time, what will it look like in the Fourier domain? So the definition of Fourier transform is this. So let us try to see what will we get. So f of k omega. So we want to find the Fourier transform of this particular function. So what we are going to do, we say that there is a function f of t and r, and it is differentiated with respect to time, and we want to find the Fourier transform of this. So Fourier transform of this function, this will be nothing but we'll just use the definition of this uh, dt d cube r e to the power I k dot r minus omega t, and the function as a function of r and t and r. Okay. Now what we can do, so this is uh, so here we need to have some particular conditions on f. Uh, we'll try to, so what we are going to do is this dt d cube r. So we know that chain rule, right? So what we are going to do is dou by dou t of e to the power I k dot r minus omega t to f of t r minus dou by dou t into f of t r. Or this is the integration by parts, whatever I'm doing now. By integration by parts, what I mean by it is, so so we have written this particular term as the difference between these two derivatives. So this entire partial derivative with respect to time minus the derivative of the first function. This is just, if you expand this, uh, what you will get is just this. The term in this curly braces are same. So what we have here is two terms. So one is the derivative with respect to this time, and so d cube r, in respect to time we have totally uh, uh, So there is integration and there is differentiation with respect to time. So it is I k dot r minus omega t f of t r. So we have to and that t equal to minus infinity, t at plus infinity. And the condition on this f, so f is some kind of function, the electric field, or it is either the electric field or the charge or the current density. So at minus infinity there was no electric field or there was no charge density, the quantity was not there, and at plus infinity it will again decay back to 0. So this term, the first term, it goes back to 0. So what we say, this type of functions, this is bounded in time, and here what we are left with is integral dt d cube r. So derivative of e to the power I k dot r minus omega t f of t r. Okay. So now, just by that argument that this term is bounded by, so f is bounded by time t at t equal to infinity, f is 0, and t at minus infinity it is 0. So since it is 0 at two different, so it is 0 minus 0 0, so this whole term it vanishes. So this term it just vanishes, and all we are left with is this single term. So it is minus dt d cube r, and time derivative of this, time derivative of e to the power I k r minus omega t, and it is just minus I omega e to the power I k dot r minus omega t and f of t r. Okay. Hmm. Now what we have is I omega are constant, they have been taken out, and we are left with integral dt d cube r e to the power I k dot r minus omega t into f of t r. You note that this quantity is our Fourier transform of f of t r. Fourier transform of f of t r, which is nothing but minus I omega f of k omega. Okay, here it is plus, minus, we got here 1 minus and 1 minus, it came up from here. Now what we are going to do is, since we know that this time derivative, uh, now we have this relationship d is equal to epsilon naught E plus P, and J is equal to time derivative of P, and we have these equations d of k omega is equal to epsilon naught epsilon k omega, and electric field at, this is the Fourier domain constitutive relationship. Okay, now what we're going to do, we'll do a time derivative of this. So if we do a time derivative of this, what we have is dou by dou t of d is equal to epsilon naught E t plus E by dou t. On doing the time derivative, what we have, we recognize that this term is nothing but j. So from here is equal to epsilon naught by dou t is equal plus j. Now if we go to the Fourier domain, what we have is, in this result, what we have in the Fourier domain, uh, if we take this as the kernel, that e to the power I k r minus omega t, then derivative with respect to dou by dou t, it is just replaced by I omega f of k omega. So what we are going, if we do the Fourier transform of this equation, so if we do Fourier transform of the entire equation of d is equal to epsilon naught plus j. So what we'll end up is, Fourier transform of this time derivative is I omega d of k omega is equal to epsilon naught I omega e of k omega plus j of k omega. Okay. Now we are going to use this constitutive relationship in this equation. So what will have now is, so we'll use j, we will substitute here, and d we will put here. Okay, so we will end up with, so I omega d will be epsilon naught epsilon k omega e of k omega, that is this left hand side, is equal to epsilon naught I omega e of k omega plus j. J is sigma k omega E of k omega. Now we can take what we have is I omega epsilon naught epsilon k omega. Oh, I'm taking everything to the left hand side. Epsilon naught I omega minus sigma k omega E of k omega is equal to 0. So this can be 0 only if this term is 0. So what is that term? So if we say that this term vanishes, so we are left with I omega epsilon naught E k omega minus epsilon naught I omega plus sigma k omega is equal to 0. And if we rearrange this, what we end up with is, so we want this epsilon k omega on left hand side and rest others on right hand side is equal to epsilon naught I omega divided by I omega epsilon naught minus sigma k omega divided by I omega epsilon naught. This is what we got. So the final relationship what we have is epsilon k omega is equal to, you see here the numerator and denominator are same, 1 minus, so this is plus. So on simplification, this is the equation or the relationship we get between uh, the conductivity. Here you see this is the conductivity and here it is the permittivity, relative permittivity, and here what we have is conductivity, or like both of them in the frequency domain. So we can do a further simplification when we are talking about the uh, so when we're talking about interaction of light with metals, that the dielectric response can be like taking in the limit So what we are now saying is that the response is the response of the material to the electric field is local. What it means is that the electric field at position say R prime, uh, it is uh, the response is happening at that R prime itself. Okay, so in that approximation we have to take k equal to 0. Okay, uh, so that will imply that we are saying that at a particular position the, so it is a spatially local response wherever there is the electric field, at that position only we are looking at the change of the response of the material. So what we are going to do is we'll put k equal to 0, or it is just independent of k now. So we will just write epsilon k omega k equal to 0 omega s epsilon omega, and similarly sigma k at 0 omega, because we know we are implicitly assuming that it is a specially local response. So we have now only the temporal dispersion sigma omega. So the relationship, and this simplification is valid as long as the wavelength in the material is significantly longer than the characteristic dimensions, such as what is the size of the unit cell of that particular uh, size of unit cell of that particular material, or the mean free path of the electrons. And this is fulfilled till up to the ultraviolet frequencies. So even if the in the UV region the frequencies or the wavelengths are quite small, but the local response is it has a resolution better than the wavelength of the UV light. So so this simplification is valid. So just to make a note of it, this simplification. So what is the simplification? Simplification, it is the we are taking the limit of spatially local response as long as the wavelength lambda of the light in that material is significantly longer than all. For example, what is this characteristic dimension? Means that the electrons are actually moving in a random motion, right? So uh, that but this lambda has to be more than that mean free path of that random motion. So let us. So this is all about today. We'll try to revise what we uh, what we did today. So we started with the Maxwell equations, and from the Maxwell equations we defined. Uh, so these equations defines the fields, the dielectric displacement, electric field, magnetic field, and the all the fields with the sources, the external charge density and external current density. Then we say that these external current and charge densities, they are like uh, so we are injecting this external charge and current densities into the system. They are like we're driving the system, and as a response of the system, the fields, the material is trying to modify the fields in them, and because of that modification, it is like how is it modifying those fields? By inducing its own internal charge and current. And from that uh, uh, so for example, when it induces its own internal charge and current, so there will be own internal fields in it, for example the polarization and the magnetization in the material, and because of that there will be resultant fields, the D and H. We saw the relationship between these fields and the sources, and we derived the material properties, the susceptibility and the electric susceptibility and the permittivity. The susceptibility and permittivity, these are the equivalent concepts. So if you know one of them, you know the other. We found another important equivalent quantity, the conductivity. Conductivity, it is usually used in the low frequencies, and the permittivity in the optical frequencies. And by using this, so we went into depth, uh, and we saw the effect of temporal and spatial dispersions, how uh, the electric field, so how this can be mathematically represented. And we saw uh, that in the Fourier domain, this this convolutions, this transform to uh, just multiplications of these frequencies. Then we took another, then we simplified, and we found the relationship between the permittivity and the conductivity of the material. And then we took the limit of spatially local response. That means at a particular position, so the response of the material to the electric field at a particular position is happening at that particular position, is due to the electric field at that particular position only, and not due to the electric field at some other location. So that is this limit of spatially local response, and it is valid up to the ultraviolet frequencies. So this is where we stop today, and in from the next class we'll go further, and we'll look into, like, for now we saw the permittivity. From this permittivity we can get the reflective indices, and this reflective indices, since permittivity is a function of frequency, and that is in turn because of this temporal dispersion, we'll see that uh, the reflective indices, the n and k values, they are also related, they are also frequency dependent. And we'll go further into the dispersion relations, and we'll use this formalism to derive what is the permittivity of the free electron gas, because at the end what we want to find is this quantity permittivity of a free electron gas which is inside a metal. So thank you. We'll see in the next class.